Atomic absorption. What is it? What does it do? And why should I use it? The problem with this lab block is that many of you will start atomic absorption spectroscopy labs without first getting to atomic absorption spectroscopy in the classroom. Because at this point in the semester, we are probably still talking about infrared spectroscopy, and we haven't made it to AA yet. So the purpose of this video is to give you a little bit of insight on this machine and what it's going to be doing and the purpose of each lab. I'll also go through what the Excel spreadsheet should be looking like with these labs as well. Okay, so first off, when we talk about atomic absorption spectroscopy, we typically abbreviate this as AA or AAS. We have an absorption method and we have an emission method. One absorbs light, the other one emits light. Think of it that way. So AAS and AES are both used. Out of the two, AAS is used the most often. The reason is because a lot of times it's more sensitive than the emission spectrum. The emission spectrum is really only used for the alkali and alkaline earth metals, and then the rest of everything else is traditionally the absorbance methods that we see. So something like calcium or something like magnesium or something like sodium is typically ran on the emission side of the instrument, and then things like copper and zinc and lead, those are typically ran on the absorption side, AA versus AE. This instrument will pick up metals. That's the purpose of the instrument itself. It is a metal-driven instrument. Any metal that we have in solution will be able to be detected on the machine. The problem is that in order to detect the metal, you have to have a matching lamp, and these lamps are abbreviated with an HCl, meaning hollow cathode lamp. That does not stand for hydrochloric acid, people. When you go through and you read a procedure or a standard operating procedure and it says something about HCl, that is standing for hollow cathode lamp in the world of AA, if they're all capitalized. So H, capital C, capital L. HCl is hydrochloric acid. That can be used in atomic absorption spectroscopy. The problem, though, is that you've got to be careful. What is it really talking about? So HCl is the hollow cathode lamp or the bulb that makes the machine work. In the first lab, varying the wavelength, we are going to be looking at copper. Therefore, we need a copper lamp in order to run this analysis. Now, if I begin to look at copper's wavelengths, what I will find out is that there's multiple versions of them. So let's think about for a minute the lab that you did with benzene. So you ran benzene on a UV vis spectrometer, and what you end up seeing was probably a spectra that looks something like this, or something similar to it. And this spectra represents that benzene has multiple wavelengths, right? So benzene can absorb light at multiple wavelengths. And we looked at these wavelengths and we picked out a lambda max, which is where we get the highest absorbance read. So let's pretend for a minute that that is my highest absorbance read. All right. That's my lambda max. That's the one that I go to read because that's the most sensitive one. In the world of AA, things are almost identical. For starters, in the world of AA, we are traditionally running between the UV vis portion all over again. So take a look at these nanometers. You look at copper, you look at silver, you look at zinc, you look at chromium, You look at all of these wavelengths for metals for the atomic absorption spectrometer, and they will be in the range of UV and visible almost every single time. So it's not uncommon to see copper maybe to measure at 324. It's not uncommon to see copper measure at another nanometer of 327. It's not uncommon for copper to measure another nanometer like 217. And all of these will be listed in what we call the cookbook. This is kind of like our CRC or our Merck or really our Sattler that we were using over here to get the organic lambdas. So this is the Sattler, right? We opened up the Sattler UV spectroscopy, we found the lambda maxes, we found the molar absorptivity coefficients from that book, and we wrote them down. Well, the AA has a book that's very similar, and we call that the cookbook. And we have two versions of the cookbook. One is a printed out copy that we use for our old Buck instrument, and the other one is an electronic copy that is built into the software of the new AA instrument from Varian. So if I look up copper, I'm going to find copper's wavelengths listed all the way down through the chart. And 324, 327, 217 will probably be one of the ones up at the very top. Well, they will list them in order most of the time, and they will list this one as primary, and we regard this one as secondary, and we regard this one as tertiary, quaternary, and so on. Well, the primary wavelength is kind of like my lambda max for the UV vis. There's no difference in them really. This is my most sensitive wavelength. So if I've got copper and that copper is in a low concentration that I want to pick up, then I go into the primary wavelength, and that will be sensitive enough, hopefully, to pick up these small traces of copper. Well, if my copper solutions may be a little high, I can overload the instrument. Just like with the UV vis, right? We saw that concentrations that are too high cannot be ran on the instrument. My absorbance reads PEG, 3, 4s, 5s maybe. We don't want that. Well, the same thing's going to happen with the AA. That's why we have secondary, tertiary, quaternary wavelengths in place. So if my solution maybe is a little strong and I'm working with a higher concentration, then maybe it's my best decision to go to the secondary wavelength and read the secondary wavelength instead. Or maybe it's just too high that secondary maybe isn't going to work for me, and maybe I need to go to tertiary instead. So how do I know which one to pick? Well, that's the linearity range. On each one of these wavelengths, you are going to see a linearity range in play. So for instance, with the primary wavelength, you're probably going to see a 5 part per million linearity range. What that means is that this primary wavelength will be fairly decent for you as long as you're running samples that are about 5 part per million or lower. If you're running 5 part per million or lower, the linear range will tell you that you will end up with a straight line. If I use the primary range and measure solutions that are 20, 30, 40, 50, 100 part per million, what I will end up seeing is a line that begins to get created in the beginning, but then it will get so high that it will basically kind of plateau off and make this curvy line. And that's not what I want, especially for linear regression lines. If I'm making a series of standards, I want to make sure that my standards are giving me an R-squared value of 1 for my calibration curve. I don't want to see these floppy little wiggly pieces in my linear calibration curve, because that won't make any sense, and I can't really use that line to do my calculations with. So what happens is that the secondary wavelength just brings everything back on scale, and it straightens the line back up because its linearity might be a little higher. Or the tertiary wavelength. The tertiary wavelengths, well, that one's probably a little bit higher. The linear range maybe goes, higher than 20, maybe 30, who knows, depending on the instrument, depending on the settings. And this will tell me the cutoff value for the tertiary setting. So that's how I determine which wavelength will be the best for my analysis. Well, in this lab, what will happen is that you will use two instruments. You will use our Buck AA, and you will use our Varian, which is now part of Agilent AA, and you will run a series of copper standards, copper STDs. And these copper standards go between 1 to probably 50, and they will be pre-made. The only thing that you have to do is set the instrument up and read the samples. You will read these standards on both instruments, and you will read them on the primary setting, on the secondary setting, and on the tertiary setting. Keep in mind that each one of these, you will often set a slit width, and the slit width is basically like the keyhole that this lamp is going to be looking through. So do we want to give it a very narrow keyhole to look through, or do we want to give it a very wide keyhole to look through? So this is the tunnel in a way, or this is the path of how wide it can be for this lamp to shine its mission or its wavelength through. So overall, that's what we're doing with the instrument. Something else that I want to keep you in mind is that we are using a copper lamp. On the lamp, we will have to make the wavelength settings. So we will have to make sure that the instrument is reading the go-to wavelengths of 324, 327, or 217. So we have to make sure that that's being taken care of. Not only that, but we also have to take a look at the milliamps on the lamp itself. We want to make sure that we are pumping the right amount of energy into the lamps so they can do their job. And the milliamps will tell us that recommended setting. So for instance, the copper lamp might say 5 milliamp optimal, but 20 milliamp max. Well, what that means is that we need to set this at 5 for my optimal readings. I never want to set this lamp over 20 because I have a tendency maybe of blowing the bulb or blowing the instrument. So this is a setting that we always have to make in the machine every single time that we choose a lamp to run on the AA instrument itself. So in the next video, I'll show you what this data will look like when you begin to do your Excel spreadsheets and what we're after when we're looking at the data. So this is in a nutshell of what the lab is all about. Running some standards, getting used to the equipment, making some data or some graphs from the data, and analyzing and interpreting what that means.